What we wanted to do for you guys today was, what's the really big thing that Nillion is tackling? And the easiest way to understand it is, one big aspect of Nillion is it represents a fundamental shift in the way that you store sensitive information, right? If we think about, say, encryption, right, which has been powering computers and powering technology for decades now, it is built on this idea that you can take a digital secret, you transform it, and then you put it in a safe somewhere. But it also means that if you have either unlimited time or unlimited computing power, you can decrypt that thing. And as computers have gotten more and more powerful, that becomes a bigger and bigger threat. Just check the news, right? Every other week, you see this massive company with a big database breach, right? Be it T-Mobile, Wells Fargo, Equifax. I mean, these are huge, huge companies. And so what if the answer wasn't about baking a better encryption? And what if the answer was, in fact, breaking the system entirely? And so that's actually what we're going to be covering here today, because at the heart of Nillion is a technology that actually uses a decentralized network to store private information. The way we think about it, it's actually in the white paper. If you've seen Harry Potter and the idea of Horcruxing, we basically take data, we Horcrux it, and turns out when you Horcrux data, it turns out to be the safest place ever and safest way ever to store something. It reaches a standard that they call information theoretic secure. And that simply means that even if you had unlimited time and unlimited computing power, even if you had a quantum computer, you wouldn't be able to break the information or uncover the information. And so this technology has been a pretty big breakthrough for Nillion. But what's really interesting is how we've taken that and turned it so that it can be something that can be commercialized. There's so many projects out there that have great technology, and just so many great technologies out there, period. But the real art that we've been working on is being able to take something that's interesting, but to actually commercialize it and to brand it and put it in a way where it can actually change the world, right? And so today we're giving you a small slice of Nillion, where we talk about why encryption is dead and the technology that's driving behind this project. We know it's a pretty blockchain heavy crowd, so we're going to push your understanding a little bit as well. This is going to be the most technical presentation we've done to university. And so for some of you guys, that's great. For others of you, if it gets too crazy, other parts of the presentation will make up for that. And then all of this is actually building up to our big event tomorrow. And so tomorrow also in Chelsea at 6 o'clock, we have this huge event pretty much next door to here. And that's 300 people. And it's basically the first time that we're going public with Nillion. The website goes live, the white paper goes live, and we've got 300 people RSVP'd for that. And so anyone that's here, we actually reserve spaces for you guys tomorrow. And so if you're interested in being part of the bigger event tomorrow, you guys are all welcome, and we'll give you guys the invite and everything. We've actually reserved the spots for you guys. And so tomorrow is, you're gonna have the likes of FTX and Andreessen and CoinDesk and everyone there. And we're actually gonna have a more comprehensive panel, but then also, some pretty great hosts that are digging even deeper into the broader technology. So, with that said, I want to introduce you guys to Miguel. Miguel is the chief scientist of Nillion, actually the inventor behind this technology that drives the entire project. The guy's got a really interesting past. He's been working in technology for the last 20, 30 years, and interestingly enough, the guy's got 30 patents under his name. 7 of them still govern the flow of data packets between internet cables. And so in 2017, he came onto blockchain and wanted to do for basically Web3 what he did for Web2, and that's when he started doing his work that drives Nillion. Actually, it took 4 years of R&D to come to a point where we were able to turn this into something that we could commercialize. And so he's going to be talking about why encryption is dead, the core technology that drives Nillion, and then from there, we'll turn it over to a panel with 2 professors from NYU to kind of really dig into the project and to ask some of the bigger questions that we've been looking at over the last few weeks and then months and then actually years in this case. All right, guys, you're in for a treat. Thanks. Miguel, stage is yours.
Thank you, Andrew. Hello, everyone. It's a real pleasure to be here. Thank you so much for coming. So we're going to be talking about decentralized networks, including blockchain, but from the perspective of mathematics, from the perspective of cryptography. So we're going to be talking about something called cryptographic primitives. Those are the building blocks with which you can build then protocols that run this type of networks. And so we're going to follow a trail of different cryptographic primitives, going from one to the next one. Each one is going to be more complex than the previous one, but also functionally richer. And we're going to end up in a nice place. It's an interesting place. It's a different approach to decentralized networks, whereby you're not talking about a blockchain. We're not talking about a chain of blocks and consensus mechanisms. It's something different with unique properties that we will also discuss. So let me start by introducing decentralized networks. Why the fuss? Why are they so interesting, and why are they, there are so many people excited about them? There's many ways of talking about this, but I'm going to talk about in terms of security. So I'm going to talk about a model, security model that is called the CIA. It stands for confidentiality, integrity, and availability. And if you compare the current internet, which is Web 2 on this slide, to Web 3, which is kind of the decentralized version of it, the difference is that the internet is centralized. So when you send data to a server, that server or group of servers is owned by essentially a company, or maybe a government, maybe an individual. But the thing is that there is one authority managing that server or group of servers. Whereas in a decentralized network, the idea is more like a living organism with different cells, all of them cooperating at the same level. There is no leader, there is no boss, there is no authority. All of them are at the same level making the decisions together. And they do that by following a protocol powered by cryptographic primitives. And so that has profound implications in terms of security. If you think about availability and integrity, Andrew already covered that. In terms of availability, it happens often that even to the best companies out there, that sometimes they have downtime because they have a single point of failure, which is the organization running that infrastructure. And also in terms of availability, which covers the protection of data against unauthorized access, you also have all these hacks. People coming in because there's just one system with the data in one place, or if it's replicated, you attack the weakest link, and there you are. You have the data. You decrypt, you break the encryption. Maybe the encryption key is there. Maybe you break encryption itself. But the thing is that you get to the data, and it happens, unfortunately, quite often. The other thing is integrity. Integrity means that once you've sent your data over to a server, you've lost control over it. That the organization controlling the server can change the data without even your knowledge, and so there is very little guarantees on the preservation of the integrity of your information. Now, moving on to Web 3, we have this network of nodes, and the nodes belong to different entities, different organizations. So there is no single authority owning all of them. And so because they're no leaders, because they cooperate at the same level, if part of the network goes down, it doesn't matter. The rest of the network will still function. And so it has high availability. And also regarding integrity, as long as the majority of the nodes are good actors and are following the protocol, you can be sure that your data won't be changed. And this is what it's called immutability in a blockchain. But what about confidentiality? It seems like Web 2, the current internet, has more confidentiality than blockchain, because you have all these accounts, user accounts, behind which you hide all the user information. So think about all the thriving ecosystem of apps and services out there. All of them are making use of this property of hiding some information so that not everyone sees everything. But somehow, in going from Web 2 to 3, we've lost that along the way, because most interesting blockchains are public. And by definition, that means that all the data that they have can be seen by anyone. So that's okay for some use cases, like maybe decentralized cryptocurrencies, but it may not necessarily be okay for others. So thinking about moving applications and services from Web 2 on top of a decentralized infrastructure, you would find problems because you don't have the concept of an account or the ability to hide information from other people. And so that's an important limitation, which we summarize here. But going beyond that, you also realize that actually blockchains were created with a single use case in mind, which is that of keeping a ledger of transactions. So it matters the value of the transactions and the order, but it doesn't matter things like computation. And so maybe if you are interested in going beyond just storage of stuff, and you want maybe even other models of storage that are not immutable. Or maybe if you're interested in processing in general, computing and processing, then or other use cases that are not related to tokens or transactions, then maybe blockchains are not optimum because they were not made for that. They can do that through smart contracts and other things, but they were not conceived for that. So the question then is that the only approach to decentralization, or is there something else? The answer is that there is something else. And so the idea with this presentation is to walk you through the series of cryptographic primitives from the ground up, each one more complex than the previous one, until we get to a set of primitives that constitute the core of what we could call as a different approach to decentralization. And now thinking about the CIA model, that decentralization still keeps the nice things about blockchain, high availability, integrity, but on top of that, it is made not just for storage, but also for processing. And it brings confidentiality from the ground up. Confidentiality is the property that supports privacy. So it's a very important one. So let's begin the adventure. Talking about cryptography. When I mention this word, maybe you're thinking about, encryption or zero-knowledge proofs. And most probably you're thinking about a type of cryptography that comes from something called complexity theory. The idea here is that there is an observation that out there, it's an empirical one, that out there there's some problems which are very hard to solve. But once you've found the solution, they're very easy to check that solution is indeed the one. And it's empirical because it hasn't been proven mathematically. This is a famous problem called P equals with question mark NP. It's a $1 million problem, so there's a price on it even. But empirically, there's a lot of evidence that seems to be the case. And so exploiting this fact or this observation, the idea here is to create cryptographic primitives by placing one of these difficult, hard to solve problems between the attacker and the secrets that you want to protect. And so that the only way for the attacker to get to your secrets is by solving that problem. That is very hard to solve. So here we have some examples of such hard to solve problems. We have the discrete logarithm. It's very hard in finite or in discrete mathematics to solve the discrete logarithm. And it's also very hard if I give you the product of two large prime numbers to find which those numbers were. So those are two examples of these problems which are hard to solve, but very easy to check, to verify. And from this, what I've done is just to mention a few cryptographic primitives that are currently used in blockchains extensively. So ECDSA is used for signatures. That's what you use when you send a transaction signed to the network. And then you would have a key exchange protocol for the communication channels between the nodes. That could be either Diffie-Hellman or RSA, which is public encryption. But the thing is that we are not saying that these primitives are bulletproof and unbreakable, because indeed, by design, there is a mathematical problem that has a solution. And so the attacker could solve that problem. All we are saying is that that problem is really hard to solve. And it depends also on the computational power, as Andrew said, that the attacker has. So maybe these problems are okay if you have a classical computer, but if you have a quantum computer, as it happens for these two problems, then they're easy to solve, theoretically. And so, it's fine to work with primitives like this, but it's kind of not perfect in the sense that, they can be broken and they depend on the computational power of your adversary. So it's not a universal concept in that sense. So a question is there something else? And if you read the title of the presentation, you may have guessed, yes, indeed, there is, and it's called information theoretic security. The idea here is to start from a different point in maths, that it's called information theory. It was founded by Claude Shannon in the 1940s, and it's a theory that talks about information, not about the hardness of a mathematical problem. And so the idea here is that we're going to create a primitive that never exposes to the attacker enough information for them to be able to reconstruct our secrets. So we're playing with information or the lack of information rather than with the hardness of a mathematical problem. And because it's independent of the hardness of the problem and therefore independent of the computational power of the attacker, they are quantum safe. Even they're safe against, I don't know, an alien civilization which was able to harness the power of 1 billion suns. It doesn't matter how much power you have. We're just not giving you enough information to do anything, to extract any value out of the messages that you see. So we're going to talk about two primitives, one-time padding, and then the other one is a form of linear secret sharing, that is ITS. But before that, maybe I'd like to give you some intuition as to what is information. Because if I told you, how do you measure information? It's easy to measure things that are physical, like, I don't know, height, length, speed. Those things correspond to some phenomenon that has a physical foundation. But information seems to be rather abstract. Is it bits? Not really. I can send you bits that contain absolutely no information. So what is information? Where is it? How can you measure it? One of the genius ideas from Paul Shannon was to equate information with surprise, something so strange as surprise. So if I told you that it's raining now in Seattle, and you know that Seattle is one of the rainiest cities in the US, and you wouldn't be surprised, and therefore the sentence wouldn't contain much information. But if I told you that it's raining in LA, then you would be more surprised, and therefore this sentence contains more information. So we have the connection between information and surprise. And the next step is to link surprise with probability. So you model these events with random variables. And the probability of an event, the higher the probability, the less information it carries, and vice versa. And that is how Shannon defined a number of concepts around information. He was able to tell you what was the information from a specific event, the information contained in a random variable, which is called the entropy, the expected value, and also things like what is the information, the mutual information between two random variables. So those are the fundamental concepts that sit behind information theory, because it's a theory that talks about information and therefore about information theoretic security, which is the cryptographic branch from which we're going to be talking about some protocols. This one is one-time padding. Now, from information theoretic security, you can create many different primitives. You can create primitives that do encryption, or that do signatures, or that do authentication, or secret sharing. This one turns to be for encryption. And so functionally, it's very similar to what you're used to. You have a secret, which is this plain message test. You have like a key, a secret password, or in this case, it's a keyword. And then you use that to kind of scramble the secret and obtain an encrypted message. The difference to classical encryption is that when I give you an encrypted message, I'm giving you all the information you need to reconstruct the message. Only that it's very hard to access that information because it's sitting behind this hard to solve mathematical problem. But in terms of information theory, you have all what you need there. Whereas here, I'm not giving you any information. The precise mathematical formulation is what you see down there. The probability of you receiving one message, let's say test, given the fact that you have seen the encrypted version, C0, is exactly the same as the probability as if you hadn't seen the encrypted message. In other words, the encrypted message does not contain any information. It's not helping you at all. So you can do whatever you want to that encrypted message. You can apply quantum computing, whatever you want. There is nothing to harness there. There's nothing you can take advantage of in order to get to the information. And that's how powerful ITS primitives are. But that primitive kind of smelled like centralized, because in a decentralized network, you expect to see many nodes. And there we didn't see not even one node. So this other primitive, linear secret sharing, is more centralized because it does talk about different nodes. And therefore, it has a higher chance to become a candidate for powering a decentralized network, like Nillion, for example. The idea here is that of a Schroeder machine. So essentially, you have a secret, and you want to share it with nodes. And imagine that that secret is printed on a page of paper, and you run it through a Schroeder machine, and you get different shreds. you give one thread to each one of the nodes. Those are called shares. And there is this nice property that says that there's this number called t+1. That is a design parameter, so you can change it. But if you get t+1 shares or more, then you are able to reconstruct the secret. But if you get t or less, then no matter what you do, you're not able to do anything, to reconstruct anything. And this is in the ITS sense. This is where the analogy to the shredder machine completely breaks, because as you get more and more shreds from a paper, you learn more and more. It's kind of a linear thing. But here you're saying that you get one share, nothing. You get two, nothing. You get t, nothing. Is it exactly as if you hadn't received any share at all, because it's ITS. But then you get this magical share t+1, and suddenly you go from 0 to hero. You can reconstruct the whole thing. So one question would be, is that even possible? Can you meet these requirements with a primitive? So let me show you that you can. This is Shamir secret sharing, a very famous primitive. And the idea here is to use a polynomial to hide the secret. So imagine that the secret is a number. If it's not, it's easy because you can map always a string or something else to a number, right? So let's say we have a secret, I have a secret and it's a number. And I want to share that secret with you. So I want to give you shares from that secret that feel this, meet these properties that we were talking about before. The idea is to create a random polynomial. Random except for the fact that if I evaluate it at x equals 0, what I get is my secret. But otherwise, it's a completely random polynomial. So the way that it works is that this polynomial has a degree t. And therefore, if you have t+1 shares, you can fully reconstruct it. It's fully characterized. So what I'm going to do next is evaluate this polynomial at t+1 points. Each one of those will be a different share, and I'm going to give it to one of you, each one. So it works because if you gather t+1 shares, you do polynomial interpolation, you reconstruct the polynomial, you evaluate it at x equals 0, and you get the secret. But if you get less than t+1, for example, if you get t, you have set t points on a polynomial, but you still have one degree of freedom that you can play around with. And that will give you different secrets. So you haven't really fixed the secret. You haven't really characterized what the secret is. And so intuitively, we are, meeting all the requirements. So this is very interesting because we have a primitive that talks about different nodes and lets you hide secrets. So let's follow this trail and let's get serious now and ask 3 important questions. With a view of watching if this primitive is going to be able to really power a decentralized network like blockchain. So question number 1 is this primitive ITS? And it better be because the presentation is about ITS, so it would be an embarrassment if it wasn't. But actually, the answer is maybe or depends. If you're working with polynomials on the real numbers, then these are these smooth curves, hilly and valleys, and you have only a finite number of non-zero derivatives. So actually, when you get more shares, even below t+1, you're learning something about the secret. So on the real numbers, polynomials are not ITS. But if you move to discrete mathematics, to finite fields, then things get very interesting because you destroy things like continuity and derivability. Things get discrete, like you don't have 1.5, you have only 1 or 2. And it can be shown that in those circumstances, Shamir is actually ITS. And to illustrate that, let me just show you what a polynomial on a finite field looks like. It's not this familiar, polynomial smooth curve with mountains and valleys and all very nice and smooth. It's something wild like this. It's completely broken. The structure of the polynomial is completely destroyed, and it resembles white noise. And that, it can be proven that it's ITS indeed. So question number 1, all good. Question number 2, it's a bit tricky. It's about bad actors, because in a decentralized network, you don't want to, have to assume that everyone is nice. There may be some nodes that are not, they're like teenagers. They're just not following orders. They're just going on their own. And so if the protocol says send one message, maybe they will send two or three or none. Or maybe they will change the contents of the message. So in those circumstances, is this primitive able to operate in the presence of bad actors? The answer is, one more time, yes, luckily. Because you can exploit redundancy. We were saying that we were working with polynomials of degree t, and so t plus 1 shares were enough to define this polynomial, but we're going to send more shares. We're going to send n, where n is greater than t plus 1. And so we're going to have redundancy. If you gather t plus 1 shares from good actors, they will characterize this polynomial. And that means that any other share from a good actor will lie on the polynomial, will be on the curve. But if it's from a bad actor, it will be an outlier, it will be outside. So you will be able to detect the cheaters, the ones that send you something back that is not what you send them when you share the secret. Those are the case for example, here of party 1, party 2, and party n. And in fact, you can use something called error correction codes coming from error theory that comes from, from coding theory, which comes from information theory. So even if everything stays in the same nice corner of mathematics, information theory. And with these codes, you can detect the cheaters, the outliers, and you can remove them and reconstruct the right result. So now we're able to process in the presence or to store information and retrieve it in the presence of bad actors. My last question is a loaded one, because that's fine. I mean, we can store secrets and retrieve them, but we want to go one step further. We want to be able to process stuff. You know, I want to share a secret with you, and someone else shares another secret, and we want to add those two secrets or to multiply them, but without you having to reconstruct them, without you having any, idea of what those secrets are. So we're going to ask for those two operations, addition and multiplication, because with them you can characterize an arithmetic circuit, and with them you can evaluate any function. So they are key to processing. And so, okay, let's see. What do you think? It's going to be a yes? You can do that or not? Yes? The answer is not, and it's really sad. It's one of those sad results. You can do additions, which is great. I mean, the addition of two polynomials will add the secrets instantly. So you locally add your shares from each one of the polynomials. You will get a share from another polynomial, which is the polynomial resulting from the addition. Everything works great. Now let's try to do it for the multiplications. You can multiply your shares locally. That will be a share from the polynomial resulting from the multiplication, but the degree of that polynomial has increased. With additions, you keep the degree constant. With multiplications, you increase it. So if you multiply two polynomials of degree t, you end up with a polynomial of degree 2t. So you need now 2t plus 1 points to characterize that polynomial instead of t plus 1. And we have a problem. We have a problem of explosion of the number of points required for characterizing the result. So with every multiplication, you're growing and growing and growing the size of the polynomials. And we've reached the end of the rope with Shamir secret sharing. There's nothing else we can do to fix this. And so we need to get another level on top of it and define yet another primitive that kind of fixes this problem. And that's what's called secure multi-party computation. So a question is, can you do secure multi-party computation with linear secret sharing that is ITS? The answer is going to be yes, for both arithmetic circuits, additions and multiplications, but also for Boolean circuits, which are another way of expressing functions with Boolean gates. But we're going to focus on the arithmetic case. And so if you think about it, and assuming that this problem with the increasing degree of the polynomials is somehow solved by this secure multi-party computation primitive, we have all the ingredients we need for a decentralized network, because we have a way to send information, share it in a very secure way. It's an ITS way. We have a way to store it. The nodes can store it in different formats. They can do it in an immutable way, but they also could do it in a way that can be edited and change it or delete it. So it's even more flexible than a blockchain. And they can process it. They can perform computations. And moreover, they can operate in the presence of bad actors with these error correction codes. Now, the error correction codes are like the consensus mechanism on a blockchain. So in a blockchain, some bad actors can be there as well. And so the way to cope with that is that the different nodes run something called a consensus mechanism. And that is a protocol that enables them to reach an agreement on the state of the ledger of the data, even when some of them are cheaters and are lying. And that mechanism requires the exchange of messages. But here we have something different, which is this error correction that can actually get the same result, which is the reconstruction of the right value, but this time without the exchange of messages. Because it's something that you do locally in your machine when you read and receive the shares, and you don't need the nodes to talk to each other. So we're talking potentially about something very fast in terms of consensus. Okay, so we were saying that we also can do processing. What does it mean really? Let me give you an example. Let's try and find out, let's imagine that we want to find out who is the wealthiest person in the room, or maybe the average wealth, or maybe the standard deviation. It doesn't matter. Each one of those are a different function. So what you do is to translate that function into a bunch of sums and multiplications, which is the arithmetic circuit. And then the way it works is that each one of us is going to proceed in 3 phases. So each one of us is going to enter our wealth, which is the secret number, into a polynomial. We're going to get the shares, distribute them, so that each one of us now, if we are nodes as well, has received a share from each one of the secrets from the rest. Then we're going to follow whatever implementation of that function is telling us. You have to do so many additions, so many multiplications. It really depends on the problem that we want to solve, because this is talking about general computation. It could be a maximum, it could be the average, standard deviation, or something completely different. And then we're going to get to a share that represents the result. So let's say that everyone wants to know what the result is. We'll receive the shares from the result, and we will apply error correction to compensate for some of you guys being bad actors. And hopefully each one of us will get the result from that function. So this is what it looks like altogether, but there is a problem. The computation requires the nodes to exchange messages. And that is the way that SMPC has fixed the problem of the ever-increasing degree of the polynomials after multiplication. So the way to solve it is to have the nodes exchange messages between them to shrink the degree of the polynomial back to t. And that is a problem, because exchanging messages for every multiplication is very slow. We're talking maybe about, I don't know, you can run 10 multiplications per second, the most. That's why we are very excited about Nillion, because we come up with a way, with a new primitive, to actually do that without requiring the nodes to exchange any message. And the difference is really huge. It's comparing the speed of a CPU, which can operate and do tens of billions of multiplications per second, to those 10 multiplications per second. So it's really 9 orders of magnitudes. It can be up to 1 billion times faster. And in fact, SMPC hasn't found wide adoption because of that problem of scalability. And it doesn't matter how you define SMPC. It can be through linear secret sharing, it can be through arithmetic circuits, through Boolean circuits, through other primitives. You always ended up in a place where sometimes nodes for some operation had to exchange messages. But in Nillion, in NMC, which is the name of our system, it doesn't happen like that. The nodes can essentially operate as if they were locally computing stuff, only that they're doing that in parallel, but they're not exchanging messages, and they get to the right result. And they have all the nice properties of ITS, they have all the nice properties of being able to run any computation, any function evaluation. And so let me try and give you some idea as to how that's even possible. The idea is that it follows an observation, which is that this linear secret sharing was being kind of burdened with a lot of tasks. It had to be correct, which means that it had to perform additions and multiplication, but also it had to be ITS, and also it had to operate in the presence of bad actors. So 3 things, kind of one primitive. It's a lot to do. It's a lot for that primitive. So as a result, the primitive could do that, but not very efficiently. So we used an approach which is kind of a divide and conquer, and we reassigned those 3 things between 2 primitives. And so we still use linear secret sharing, but it's only for the functioning in the presence of bad actors. And then we use a new primitive, which is one-time masking, which is very similar to the one-time padding we saw before, about getting a secret and then using some randomness to kind of hide that secret. But this time is with a different operation and with something that we call blinding factors. Is the name we give to this randomness. And the thing is that we can design that primitive because it doesn't care about the operation in the presence of bad actors, because that's taken care by the LSS primitive. We can design it to be very efficient and to be able to perform multiplications and additions without internode communication. And so another element is that both primitives need to be ITS. So there is a place for them to be linked together. And so that the tandem of them, the pair of them, is altogether ITS as well. That's a very important element. So a closer look at this is to look at the process of me now sharing a secret. Before it was using a polynomial, hiding it in a polynomial, giving you evaluations from that polynomial. Now, there is the blinding factors, which are the thing that are going to hide the secret. But those blinding factors are going to be hidden themselves through the linear secret sharing. So I'm going to use the polynomial not to hide the secret, but to hide the blinding factors that are going to be used to hide the secret. And so I'm not going to be asking of the linear secret sharing to do additions and multiplications. I just needed to store those blinding factors and to be able to retrieve them. And that's it. What I'm going to be using the primitive that I'm going to be using for the additions and multiplications is the other one, is the OTN, the one-time masking. So the way it works is I recall the shares, which are the evaluations from the blinding factors. I run error correction. I get the blinding factors, and then I use the OTN primitive to blind or to mask the secret, and I get what we call a particle. And then I send those particles back to the network. And so now the nodes have two things. They have shares from the blinding factors, and they have the particles, which represent the data. Now you want to add and multiply secrets. All you have to do is add and multiply particles, but locally, without communication. And therefore, it's really fast. So just to summarize, we've seen that encryption is coming from a corner of cryptography that is based on the hardness of some mathematical problems. And that's cool, and you can do a lot of interesting things with that. But the thing is that you're assuming that the problem is indeed hard. You're assuming that your attacker is computationally bounded, and the primitive has a way to be cracked or solved because it's a mathematical problem that has a solution. We saw a different approach on that, which is ITS, which is about not giving the attacker even the chance to do anything because they don't have information. So it doesn't matter if they have quantum computers or anything like that. It's completely irrelevant. And it's what is technically called an unbounded, computationally unbounded adversary. And then we saw this nice primitive, Shamir secret sharing, a lot of potential. We asked 3 questions. It was able to answer 2. But then there was this other question about the computation, and it didn't really work. So we had to go one level up and fix that problem with the multiplication. We had to create a secure multi-party computation primitive. But then we jumped into another problem, which is the communication between the nodes, which makes the thing really slow. And then we showed that by combining 2 primitives and dividing and conquering, we can actually solve that problem and create a new approach to decentralization that can really function as if it was a centralized network, essentially, at the same speed. And we think this kind of opens, it's like a green field of opportunities, because now you can think in terms of storage solutions, computation solutions, way beyond transactions and way beyond just ordering of a ledger. Essentially, you can think in terms of Web 2, like anything you can think of, any service, could now, in theory, be translated and implemented on top of a decentralized infrastructure like Nillion. And you have the same advantages as you have before, which is from a blockchain perspective, which are availability and integrity, but you also have the nice things from a centralized architecture, which are primarily speed And you have a new feature, which is the ability to work with private information, with sensitive information, without disclosing it. It's something that not even centralized networks typically have, because they typically use standard encryption, and you need to decrypt information to process it and then encrypt it back again. And so you have a very interesting combination of unique properties. And yeah, and that's why we are so excited about Nillion. Thank you very much.